is our first lesson on financial applications. We're going to be talking about simple and compound interest. So the goal today is to make connections between investment interest and sequences and functions to better understand financial growth. So we're going to be looking at the simple interest, how it's like a linear arithmetic sequence, and then compound interest and how it's kind of like an exponential, and comparing growth of simple and to compound interest. Um, and so some of this is going to be done in the homework, making connections on your own. We'll do some examples together. So first off, just asking the question, if you had $500 and you're loaning it out 10% per year, how much money would you have if you um, loaned the money for 5 years and the person paid you back every year? So they paid you back what money it gained every year. Um, versus if they loaned you out 5 years and the person didn't pay you back until the end of the 5 years. And so for the first one, so the idea of interest is actually just the amount of money that you earn on money. And so it's really the percentage growth that the money has if you are borrowing money or the money that you owe grows, or if you're investing money, the money that you invest grows. So first one is you're adding 10% each year. 10% of 500 is just $50. So we're adding $50 every year. So we're going to add $250. The money doesn't stay in the account, so it's only $50 every year that you get back. And so you get a total of $750 with the original 500. So the question was, how much money would you have? So the next one, you loan money for 5 years. Person doesn't pay you back right away. So here we're going to multiply by 10% growth each year. So now we're multiplying by 1.1. If we multiply by 1.1 5 times, you get 805.26. And that's the total, including the interest. And so you can see that this second thing is what we're going to call compound interest. And we can see what it looks like here. When graphed simple interest, the first one would actually be a line. And so we're just adding $50 every time. So we can see if you start at 500 and keep adding 50, after 5 years, you're at 750. Compound interest is going to actually be an exponential. So it's actually going to be a curve that's growing by 10% because we're multiplying by the same amount each time. So that's that common ratio, similar in a geometric sequence. So we're starting at 500, and after the first year, we're at 550, and at the fifth year, we're at 805.3. I think this is so interesting because the amount at the beginning and the amount at the end of the first year are the same in the simple interest and the compound. But if you zoom in on the graph, that does mean that the red line, so the simple interest line, which ends up becoming higher over time, is actually higher in the first year. This might allude to like how should you calculate interest when the exponent is less than 1? It's a good question. It's just really interesting. So what is the same difference about 5 years of $1,000 at 8% simple interest versus 8% compounded annually? And so this wording compounded annually, we'll look at it more in the next lesson, but it's just saying like in 8% per year, and it's compounded every year. So it grows, the money grows and it stays in the account. So things are the same, so it's 8%, similar. 5 years is the same, $1,000 originally. Same at the end of the first year. It's going to be the $1,080 at the end of the first year. Some different things. Simple interest is going to be adding $80 each year. Compound interest multiplies each year. For compound interest grows on interest versus simple interest is just on the original 1,000. So the money that the 8% of the 1,000 is the same amount every year. Simple is linear and compound is exponential. And then at the end of the 5 years, the compound interest is going to be much higher because that curve is just going to create separation between the line. An example, describe the investment that is represented by the formula. So where f of x is the amount after x months. So I just want to connect this back to function notation. Um, because looking at a linear function is actually probably more helpful than looking at an arithmetic sequence. Although, like, we are going to come back to a geometric series when we talk about annuities. But it's a little bit more helpful because the y-intercept is a little bit more clear. We don't have that shifting to the right. At the beginning, we want to look at the $500. So we're actually starting, like, the initial amount is $500. Um, and this investment's increasing by $2 every month. $2 every month is actually a 0.4% increase. So 0.4% of $500 is $2. That's per month. Now everything is quoted in years, so if we multiply that by 12, we can say 4.8% per year. And so to describe it, we just say $500 was invested at 4.8% simple interest. This little table here, just a screen capture. I didn't put it in the nearest penny, but we do have just a little bit more accuracy here. So we notice that the common ratios are the same every time you multiply by 1.05. And then if we use the exponential equation, and just for one of these points, sub 4489 in and the number 12. So after 12 like compounding periods or 12 years. If we divide by 1.05 to the 12, we get $2,500. So describing the investment, $2,500 is invested at 5% interest per year. And this would be compound interest. And I forgot to say that there, but it's 5% compound interest.